Thank you so much to the organizers for the invitation to present my work here. And I have to say, it's an extremely weird feeling to be, at a conference in person presenting a talk. So let's see if I actually remember how to deliver and talk in person and not through a Zoom call. So yes, and I really like this idea of hybrid conferences. So I really hope that this is not just something that happens while the pandemic is here, but that is something that one way or the other survives for the future. On the one hand, for people who, for whatever reason, cannot really travel to conferences, or also so that we can look after our planet a little bit better. So hopefully this can stay for the future as well. So having said all of that, what I'm going to try to introduce you to is some modern perspective on the phenomenon of steering, which is something that actually was, people started thinking about that back in the 1930s. So I'm going to try to walk you through some ways to think about it that have been developed in the last 1 or 2 decades, including work that we are doing at ICTQT. So ICTQT is a new center that has been opened at the University of Gdansk in Poland. So if any of you is interested in what we do, please visit our webpage, and we'll be really happy to have you come visit and learn about us. So yes, I work there, and let me try to tell you a bit about steering. So steering is one possible scenario, physical scenario, experimental situation in which we can assess the non-classicality that we can observe in nature. So what do I mean by this? Well, usually the kind of two things that we have in mind when we think about, this sort of quantum experiments that present some weird features of nature, we have things like entanglement in our head, where we have, for example, two parties, Alice and Bob, and they both have full access and can characterize, the quantum systems that they have in their labs. And the question is whether, the global quantum system, the joint system that they have, is actually something that is could admit some kind of classical correlation between the two states, or if it's something that needs to be truly quantumly correlated. So that is somehow, the kind of things that we have in mind when we think about entanglement. And on the other hand, we have somehow the totally opposite extreme in this big, plethora of experiments that we can have, which is a kind of Bell non-locality scenario, where we have, two parties, Alice and Bob, which are also separated. And now what they want to do is they want to study the correlations that they observe between the measurement outcomes of the measurements that they perform on their share of the systems, which, they don't really want to think of anything of the properties of this system that they're measuring. The only information that they are relying on is on the choice of on the classical variable that denotes the choice of measurement, and the classical variable that denotes the measurement outcome that they've obtained. And so those correlations, so this is which is, just among classical variables, that is the object that we study in a Bell scenario. So a steering scenario is something which is a hybrid between these two. So now the parties have different roles. On the one hand, here we have an Alice that treats everything as a kind of a black box, and the only information that we have in her wing of the experiment are the classical variables that denotes the choice of measurement that she performs on her share of the system, and a classical variable that denotes the outcome that she obtains when performing a measurement. But on the other hand, now Bob doesn't have that kind of doesn't behave like that with his wing of the experiment. What he does is he actually characterizes the quantum states that he has, he's holding in his hands in his lab. So that kind of hybrid scenario where Alice and Bob have different types of tasks that they do with their share of a system is what we refer to as a steering experiment. And why? Why would we care about studying such a scenario in between entanglement experiment and a Bell experiment? Well, on the one hand, it's a possible situation, so why not? We are very creative people that come up with very weird situations, and we are very enthusiastic about pursuing them and see where they lead us. But also, as we will see in a few slides, sometimes this actually represents like best case scenarios for real situations. And the kind of things that we are interested in when exploring this are, well, there are many, but the two that I would like to bring to your attention are trying to understand nature, so trying to see if by studying these hybrid scenarios we can learn something more about nature that we couldn't by studying the other two scenarios that I mentioned before. And also to try to devise quantum information processing tools, so ways to leverage this kind of resources, as we will see later, to try to perform tasks. So this is kind of in a nutshell like some like why and what for we could care about this. And first, like before like getting into the talk, I kind of want to make two remarks. The first one is about what we steer, because there are always different ways that one can like think of the steering experiment. So I want to make sure that we're all on board with the particular way that people pursuing this kind of research have in mind. Because, you know, if we have like a classical system, then we could think of, you know, well, we have this classical thing going on and we want to fix, you know, this classical theory as the thing that is underpinning our experiments. And so that, you know, when we perform like this kind of remote preparation kind of experiments, the things that we are preparing in Bob's lab are actually the type of systems that this theory can have. So in classical theory, we can prepare classical systems in Bob's lab. If we think, for example, for those of you who have heard of box world, then a particular way to do steering at box world could be Alice performing some measurements in her share of box world state, and then a box being steered in Bob's lab. But there's also another way to think of steering, which is you do not fix an underlying theory, and then what you would rather do is to think of fixing the system type that Bob has access to. So we do not, you do not base or assume that you have a particular theory underlying your experiment, but the only thing that you want to assume or you want to know is that Bob has, for example, in our case, a quantum system. And a particular system type could be a quantum system of dimension 2. And this is the kind of thing that we're focused on. So in a steering experiment, Alice has these classical variables on her share of the lab, on her share of the experiment, and Bob always ends up with a quantum state in his share of his wing of the experiment. And the kind of thing that we don't want to think about are the underlying theories that underpin this experiment. And this might sound very, very confusing, but hopefully towards the end of the talk, you will understand a bit better what I tried to say with this sentence. And usually I'm asked why would you try to think of such a very weird way or peculiar way to define an experiment? And well, we've seen that somehow quantum theory manages or succeeds at explaining experiments that we have come up with so far. So there is some kind of reason why maybe we would like to think that quantum theory has a validity at a certain limit, but maybe we do not want to assume that that particular validity of the theory holds at the global level. So we maybe want to stay open-minded and say, well, we might have a theory of nature that can have some yet to be defined form, but when we want to probe things locally in our lab, then things might admit a quantum explanation. So this is, something that you can try to have in, the back of your head if it helps to try to follow the talk. And then the second remark that I want to do is maybe more for those of you who are more inclined towards information protocols and trying to, devise games or information tasks, which is, the concept of device independence. which at the end of the day boils down, for those of you who work, for example, in cryptography, to a question of trust. So for example, in a Bell scenario, what we have is, Alice and Bob, there is a source which prepares a system and, distributes them to Alice and Bob. Like, I don't know, it could be a source that prepares a pair of entangled photons that go to each of the labs. And here, the kind of thing that we're interested in, like I said before, is this conditional probability distribution between the outcome of the measurements that Alice and Bob obtain. And here, like in this kind of black box devices, then we don't trust anything in the labs. The only thing that we want to rely on is in the information of these classical variables, but we don't want to make any assumptions on the particular inner workings of the devices. And then when we have this kind of very paranoid, mindset, we can do actually really good things. We have like highest standards for security when we want to do some cryptographic tasks. But of course, these kind of experiments then become very experimentally demanding, and at the end of the day, sometimes we have low success rates for the tasks that we're trying to perform. So now, one can relax, for example, such a paranoid approach to life in one of the wings of the experiment. And in this case, then, the object that we would study are not conditional probability distributions between classical variables, but rather sets or ensembles of quantum states. So this collection of sigmas of A given X, which are the quantum states that are remotely prepared on Bob's lab, or seemingly remotely prepared in Bob's lab, by Alice performing measurements on her share of the system. And this thing here, this object, this ensemble of ensembles, is called an assemblage, which I forgot to write here, and the reference for that to Matt Pusey's paper, who introduced the jargon for that, will appear later on in a different slide. But the thing is that if we take this approach, then, well, we don't trust anything on Alice's wing, but we do have some trust on what Bob is doing. We trust that he has, like a very precise lab, and that he can characterize what he's doing, and, we want to rely on the information about the particular quantum state that he has access to. And if you do that, then, well, you don't really have any more these highest standards for security, so there are some things that you need to start trusting some, but then your demands on your experimental setup are decreased, and you have like a better success rate at accomplishing the tasks that you want to perform. So an example of when, something that you can think of is you have a bank, and the bank wants to, have some kind of communication or do something with the client. And you don't want Alice, the client, to have access to a very full, powerful optical lab in her apartment or in her student accommodation in order to do this. So we just don't want to trust anything that she does. We just want her to be able to put classical data in her phone to do home banking. But Bob, who is the bank, we can assume that, they have loads of resources and money, and they can have a quantum optics lab running in the basement of the big building. So, there are some situations in which this kind of asymmetry is not totally unrealistic, but one could try to argue for it. And this is, the fully device-independent scenario, and this is the one-way device-independent scenario. So in that way, we would be working not in the device-independent way, but in the only one-way device-independent way. So after having confused you with so many remarks and caveats and disclaimers, let me try to explain what, steering is. So in a very traditional, simplest steering scenario, you have a source. For example, here we're going to focus on quantum steering, so don't worry about anything beyond quantum yet. And here we have a quantum state, a quantum system preparing a certain state distributed to Alice and Bob. And then the way that this, Bob's system is, seemingly remotely steered by Alice is arrives in this way. So basically, Alice performs a particular measurement of her share of the system, and that, Bob's the reduced state of both systems ends up in a particular density matrix. And this is, it's unnormalized density matrix because it contains the information on the probability that Alice obtains a certain outcome when she chooses the measurement. And the thing is that this assemblage here, this collection of remotely conditionally prepared states, will be steerable, or steering will have been demonstrated if it's only compatible with a scenario where this rho B needs to be entangled. So if we could find an alternative explanation for this collection of states that does not require a entangled state there between Alice and Bob, then steering will not have been demonstrated. And assemblages that are not steerable are those that are said to admit a local hidden state model, which is the analog of a local hidden variable model for Bell scenarios. So let me maybe dig a bit deeper on what that means. So in this case, this would be a depiction of an unsteerable assemblage. And let me give you maybe 3 different perspectives on how to, understand this. And linking to what I said before, then an unsteerable assemblage is one that arises or that may admit an explanation by Alice and Bob sharing a separable state. So in that case, the assemblage would have this particular form where this is just, at the end of the day, the conditional probability distribution of Alice's classical variables on her wing of the experiment. And then another way of thinking of this is that, well, an unsteerable assemblage, you can think of it as a classical quantum state preparation source. So they have a source that sends a classical variable lambda to Alice's lab and a quantum state rho lambda to Bob. So it's a source that, prepares that kind of states. And if that's the case, then the result of this experiment would be that expression there, which matches with the first one. And then yet another equivalent expression is to think of an unsteerable assemblage to be one that arises by by creating this via a local operations or shared randomness protocol. So you have a classical source that prepares a variable lambda, distributes it to Alice and Bob, and so the state preparation of a quantum system in Bob's lab will be correlated classically via this lambda to the response function of Alice's device here. So those are different equivalent ways of understanding explaining what a unsteerable assemblage or a local hidden state model is. And so what we have at the end of the day is this. So here we have in this gray area here, the set of assemblages that admit a local hidden state model, and green here, set of assemblages that do not. So they admit a quantum realization, but they do not have a explanation in any of these ways. Mm-hmm. And now, there's the question is, well, if we have a assemblage, then how can we tell if it's steerable? Well, actually, that is unlike in the case of Bell scenarios. We can think of inequalities, but then since this is not a polytope, it's a convex set, we will need an infinite number of inequalities. But yet that is something that you can try. So you can find steering inequalities, which are the analog of Bell inequalities, and think of those also like games that you can play. And alternatively, you can also look for an explicit local hidden state model. And that actually, asking whether an assemblage has a particular local state hidden model, a local hidden state model is a semi-definite program, a single instance of a semi-definite program. So that is not a computationally hard thing to do, fundamentally speaking. And this kind of gap here, the existence of these quantum assemblages that do not have a classical realization, has been used to perform different tasks or have, some quantum advantages and things. And here are just some examples of where these steerable assemblages have been used. For example, you can use them in quantum key distributions, and you can come up with protocols where the key rates are higher and the detector efficiencies that you need for your protocols are lower than what you would need for if you would use a device-independent approach to it. Also, you can use assemblages to perform randomness certification. You can also certify incompatibility of measurements. And then you can also perform protocols of secret sharing, which is a task where a dealer, for example, sends a message to two players who cannot decode the message on their own, but they need to get together and collaborate if they would like to do so. So this is, the kind of things that you can do if you have access to this quantum steering. But like I said before, sometimes you don't want to specifically focus on whether an assemblage has a quantum realization or not. For example, in the case of Bell non-locality, whether the correlations that you see in your lab have a quantum realization or a classical realization, but rather you want to somehow go beyond and see other possibilities, explore something beyond what quantum theory can give you, and you want to see how that may or not compare to what you can see in the lab, or how that teaches you things about the quantum observations that quantum theory would predict. And it's, this whole research field of seeing possibilities beyond quantum is, there are usually certain mixed feelings about that. Like, there are, quantum theory is has been so good so far at explaining everything that we observe, at least, with the accuracy that we have, that it's kind of, some people, or, there are big parts of the community that, within, they are right to say that they haven't found yet a motivation to try to look beyond quantum theory. I have the feeling by the talks that we have heard yesterday, and the panel about quantum gravity that we had yesterday, that maybe some ideas of how to maybe of the need to try to sometimes or potentially in the future move on from quantum theory is something that is in the mind of the audience of this conference. So maybe motivating study beyond quantum is not that necessary. But yet, I would like to quote a few reasons why I like this. And actually, I find this quote extremely amusing. So we know Michelson, who won the Nobel Prize. When was it? In 1907. And back in 1903, he wrote this quote in one of, I think it was one of his books, and said, let me read it out loud. "The more important fundamental laws and facts of physical science have all been discovered, and these are so firmly established that the possibility of their ever being supplanted in consequences of new discoveries is exceedingly remote." So this is something that Michelson said when he was convinced that classical physics was the end to everything. And this was 2 years before the photoelectric effect was witnessed in the lab for the first time. So I really like to remind myself of this, to keep an open mind, to say, well, even if quantum theory looks really, really good at this moment, it might be that eventually it's not. And it would be good, to at least have entertained the ideas of how to go beyond quantum theory, so that we're not so unprepared when the moment comes, or should the moment come. And then the other reason is that I also see value in exploring possibilities beyond quantum. If anything, to understand quantum theory better, and to understand what are the limitations and how far the theory can go. So hopefully I've convinced you that trying to study things beyond quantum is a slightly fruitful topic. And hopefully in the remainder of the talk, I can try to explain to you or show you a particular way to open the door in a steering experiment to allow for other theories beyond quantum to come into play. And how much time do I have? Okay, good. So, yes, I'm so excited about giving the talk in person that I think that I'm just talking more than I would otherwise. So, in order to tell you or to mention to you a particular way to do this for a steering experiment, let me maybe first make like some narrative of a Bell experiment that is something that we're more familiar with. So in a Bell experiment, we have the source that prepares some system and distributes it to Alice and Bob, and these are the correlations that we observe. And here, because Alice and Bob are distant parties that we assume perform space-like separated actions on the share of a system, then a natural assumption is that the no signaling principle applies, so Alice and Bob cannot communicate to each other instantaneously. And what that means mathematically is that this object that we are studying here needs to fulfill these two linear relationships. So basically, here, Alice's outcome cannot depend on Bob's choice of measurement if we forget about Bob altogether in the experiment, and vice versa. So if we think about this, then in this Bell experiment, what we have is like, in this setup that I presented, we have the object that we study, which are these correlations, and the most generally allowed object are those that satisfy the non-signaling principle. Like at this moment, we don't have anything else that constrains us here, that constrains our freedom here. So after having identified that, we can totally forget about the source, and we can just study the possible correlations that you can observe just following this, these physical or operational constraints that our setup has. And once we have that, then, well, you can come up, with pen and paper and define examples of correlations, such as the famous PR boxes, that satisfy this no signaling principle and, however, do not admit a quantum realization. So once we've done this step, then we can start thinking of correlations that go beyond what quantum theory can do. And that's how, in Bell scenarios, you have this like inclusions, a set of correlations where you have the big non-signaling ones that are the ones compatible with these operational constraints, and then you have the quantum ones, which are strictly smaller, and the classical ones, which are strictly contained within the quantum ones. So let's try to do something similar for steering. So we have this scenario, and this here, in this particular bipartite scenario, the no signaling constraint is that just when we forget about Alice, then the marginal state in Bob's lab does not depend on her choice of measurement. So from here, the object is the assemblage, so this set of conditionally prepared states, which the name was given by Matt Pusey a few years ago. And then the most general allowed object is an assemblage that is compatible with the non-signaling principle. So now, if we're here, we can forget about the source, and we can just ask, well, if now I have, a particular dimension for Bob, and I have a particular set of conditionally prepared states, would they also admit like a quantum realization in the sense of, quantum assemblages that I was defining a few slides ago? Or could I have something that does not admit a quantum explanation, like the PR box in the case of Bell scenarios? And, well, this allows us to pose the question, which does not have a very, interesting answer. In this bipartite scenario, the answer is no, like everything that satisfies non-signaling admits a quantum realization. And if you want to blame someone for that, you can talk to Nicolas Gisin here in the audience, because it's this is just a consequence of one of his results, and also from Houston, Joss, and Wouters from about 30 years ago. But the good thing is that if you move on from this traditional bipartite scenario and you have multipartite steering scenarios or modified bipartite scenarios, then the answer is yes. You can come up with assemblages that satisfy the non-signaling principle and, however, do not admit a quantum realization. And this is something that from multipartite scenarios, we realized that about 6 years ago, and it was only recently that we understood how to modify bipartite scenarios so that post-quantumness could sneak into steering experiments. And some scenarios, for example, so that you can have an idea of the kind of scenarios I'm talking about, are multipartite steering scenarios where, for example, we have two black box parties and a Bob. Then in the bipartite scenario, there is the so-called Bob with input scenario, where now Bob can influence the state preparation of the quantum system in his lab by choosing the value of a classical variable. And then there is also the so-called instrumental scenario, where the way that this state preparation in Bob's lab is modified by the choice of a classical variable is actually conditioned on the value of Alice's output. So these are different types of steering scenarios where you can see some post-quantum phenomena happening. And look that we always have quantum states in Bob's lab. So in this situation now, we are kind of in a similar place to that of the Bell case. So we have the set of local hidden states assemblages, so the ones that admit a classical explanation, so to say, the ones that admit a quantum explanation, and you can prepare in your lab with quantum resources, and the ones that satisfy non-signaling principles, but however, you could never prepare them by just having access to quantum systems and measurements. And now the question is, well, given an assemblage, how can you tell if it's post-quantum or not? You know, like the big question. And we don't really know how to do it. So a useful but not complete tool is steering inequalities. Like if you have steering inequality and you know what the maximum quantum violation is, for example, the analog of Cyrelson's bound, then you can try to do something, but this is not a complete answer to the problem. And if you think of these sort of multipartite scenarios where Bob has no input whatsoever, so it's just like this traditional thing, there is actually a hierarchy similar to the MPI hierarchy for Bell, but for those steering scenarios, that was developed by, the name has escaped my mind, but in the context of extended non-local games. It was a few, like maybe 6 years ago or so. So there are some tools out there, but there is no complete package. And in order to maybe give you a bit more flavor, like some more concrete examples of what this post-quantumness is like, I'm going to present quickly two examples of post-quantum steering in this particular Bob with input scenario, which is one of my favorite toys at the moment. So here, remember that we have an assemblage that Alice steers Bob, and the Bob can influence the state preparation of his system by choosing a classical variable there. So here, the non-signaling conditions that we have go both ways. So Alice cannot signal to Bob, which is captured by this condition, and also Bob cannot signal to Alice, which is captured by this condition here. So one of the main results that we had is that you can find post-quantum steering here. And kind of a straightforward example, if thinking, after we found it, is to define a collection of positive, positive semi-definite states in Bob's lab in just the simplest scenario, and Bob having access to a qubit. And this is just a mathematical way of just presenting a particular example of an assemblage there. And the thing is that if you allow now Bob to make measurements on these states that he has access to, the correlations that Alice and Bob would obtain or would observe would actually be PR boxes. And because the correlations that they observe do not admit a quantum realization, then this assemblage could not have admitted a quantum realization to begin with. So that is kind of like a first step towards saying that there is a very simple toy example of how something post-quantum can happen in the lab. However, this is a bit sneaky because at the end of the day, we relied on PR boxes to, show post-quantumness. So you might think that, well, at the end of the day, everything boils down to Bell post-quantumness in a way. So we have another example, also in the same scenario. And the idea is the following. So this is actually, you need to go a little bit beyond the simplest scenario. So Alice has now 3 choices of measurement. And you can define a particular set of conditional states that are all, a normalized quantum state and satisfy all of these normalization and non-signaling conditions that I was telling you about. And the thing is that we want that this assemblage to be post-quantum. We want to show that. And we also want to show that if you perform like, the same trick as before, that every correlation that you can obtain between Alice and Bob would always admit a quantum realization. So something that so we want an assemblage that is not quantum. However, if Bob was to use it for a Bell experiment, everything, all of the correlations that we will obtain would admit a quantum realization. And the thing is that you can prove those two things by realizing that this assemblage admits a very useful mathematical form, which is that it may be expressed as a positive but not completely positive map acting on a quantum assemblage. So this is just a convenient way of writing that. It's not a way to prescribe a preparation of the assemblage, by the way. And then the thing is that now if Bob was to measure his system, then one can see that just because this is a positive but not completely positive map, the action at the end of the day, is just the dual of the map, and then you can define new measurement operators from it, and everything has a quantum realization. So mathematically, everything, all of the correlations that you have are quantum. And in order to test or to certify that it's post-quantum, then what we use is steering inequality, which is similar to a Bell inequality, or just similar to a Bell functional. But now instead of coefficients here, what we have are operators, and we take the trace to then recover a number. And basically what we did is to find an inequality. So we found these operators here, such that we showed that quantum assemblages always give a value higher than 0.4. However, this particular assemblage that we defined here gives a value of 0. So here we have an example of an assemblage that cannot arise by performing measurements on a quantum system and CPTP maps on Bob's wing of the experiment. However, the correlations that we can observe are admitted quantum realization. So this is like somehow a way to address the question of whether there is something new about studying post-quantumness in steering scenarios, or whether everything is actually captured by post-quantum Bell non-locality. And well, the answer is the former. And so there are various different things that one can do here. So basically, what I tried to do is to introduce you this modern formulation, there we go, of a steering experiment, how we see it from the point of view of quantum theory, what are the things that you can do with these quantum assemblages, how you can open the door for post-quantumness to be included, and how post-quantum assemblages may arise in this setup. So that's, what I've been telling you so far. And this is a relatively new thing. So there are like lots of questions that one can pursue. And actually, for those of you who are interested, in like the shape of the different sets of correlations, a set of assemblages, and technical details about how to compute or study different sections of it, I recommend you to go and check the latest works by Paweł Horodecki and his group, who have been working on trying to learn from the border of non-signaling assemblages. What I'm most interested in is post-quantum steering as a resource. So maybe let me briefly mention three important remarks that I have in my mind about this post-quantum steering. So the first one is, well, the fact that I've mathematically defined, or I say, oh yeah, there is this post-quantum assemblage, is really cool. It doesn't really mean that it makes sense to study it, because if it's totally unrealistic, if there's no physical theory whatsoever that could ever give rise to it, then there is no point in considering it as a valid candidate for the future, right? Just forget about it. So that is the first question, is this just unrealistic, or could it potentially manifest in some physical theory that we could come up with in the future? And what we proved is that, well, no to the first question, yes to the second question. So we defined a GPT, a generalized probabilistic theory, that admits post-quantum steering. And it's called WITWORLD, and my student Paolo Cavalcanti has a poster on it, so feel free to go and visit it. Then the second one is, well, can post-quantum steering be a more resourceful object than quantum steering, or in the non-trivial sense, because, well, I have a post-quantum assemblage, I can produce a PR box, I can do everything that I want to do with the post-quantum Bell non-locality. Well, can we do something that does not rely on that? And the answer is yes. We found a task, which is remote state preparation. That is a task that does not rely on Bell correlations. However, if you have access to post-quantum assemblages, you could perform it better than with just quantum resources. And that's also something that Paulo can tell you more about. And then the last thing that I wanted to mention is, can we quantify quantum and post-quantum steering? So if we want to think of steering as a resource, can we find a way to quantify it and study it like in a rigorous way? And there have been some work about it for bipartite scenarios using one-way LOCC as the set of free operations, but that doesn't actually generalize to these other scenarios that I was telling you about where post-quantumness actually arises. So what we've been doing with my student Beata Schiavin is to develop a resource theory of this more generalized steering under LOSR operations. And she has a poster also in this conference, so if you want to know more about that, then feel free to go and visit the poster in the next session. So to summarize, what I've presented you is what I tried to convince you about, is that steering scenarios are a nice way to learn more things about nature. And that if you want to try to search for steering beyond what quantum theory allows, then you need to either go to multipartite setups or generalized bipartite setups. And also steering is independent of post-quantum Bell non-locality, so post-quantum steering is an interesting phenomenon on its own right. And of all of the different questions, because there are like an infinite number of questions that one could pursue, I just want to highlight the three that I'm most interested in. The first one is activation. So can we like somehow promote, like take a post-quantum assemblage and do something, some protocol or something, which is not just a measurement on it, that then will reveal its post-quantumness at the level of some kind of Bell correlations or so. Also, like, there is the question as well, now that we have this quantum post-quantum divide in steering scenarios, can we somehow use this to explore principles or ways to somehow constrain from an intuitive way the limits of what we can do with quantum theory? And also applications. So I mentioned that we have this remote state preparation application where we have post-quantum steering as a resource, but it's more like a proof of principle sort of thing. I don't really expect it to be something that could potentially, revolutionize remote state preparation. So I think that's the question of how to use post-quantum steering in a more sensible and in a more like relevant task is something that is still an open question. So before I finish the talk, I just want to introduce you to the people that actually are doing all of this work in the background, which are the people in my group. So there is Martin Karczewski and David Schmidt, which are the postdocs in the group, and also Paolo Cavalcanti, Beata Schiavin, and Vinicius Rossi. So if you want to know about more about what we do, you can visit our webpage, Foundational Underpinnings of Quantum Technologies.eu. And yes, that's all for today. Thank you so much.
So we have time for questions. Costantino, are there online questions? No? Okay. Questions from, yeah, you can start.
Yes, thanks for the talk. I had a question about this. I was quite interested in this, one of this last remark about the principle to derive quantumness. Could you comment a bit on that, or do you have some idea on this thing?
Not really. So at the moment we're trying to, so you know that for Bell scenarios there has been a lot of research on this, and people have come out with huge plethora of principles of different flavors to try to characterize quantum correlations, and it's still not actually quite there yet. And for steering, at the moment, I don't know of any principle that has been proposed. We have,
for instance, how would you work with this difficulty of the fact that you have a quantum characterization on one of the parties? So how would you go around to have some sort of principle that is not formulated in terms of quantum mechanics?
Yes, it's extremely complicated. With my student Vinicius and Matti Hoven, we've been trying to actually tackle this question for the past year or two, and so far we don't have an answer. So I think that is the first obstacle to try to formulate these principles, how to somehow take into account the quantumness of the state so that it doesn't, at the end of the day, boil down to just another principle for a device-independent scenario.
Okay, thanks.
Okay, so maybe Renato first.
Thanks for your talk. I have a rather general question. You mentioned, or you actually gave a reason why we should be interested in post-quantum scenarios. And as you know, I'm very interested in post-quantum things. But for me, the reason was usually actually to find out why or what are the principles that single out quantum theory. And for that, it's of course useful to understand quantum theory within the framework of more general theories. But you said something differently. You said you should somehow be prepared for a potential future theory which goes beyond quantum. Now, this is kind of a different purpose, and I'm just wondering what your view is on that, of how realistic it is to actually be prepared. Because one could say, in view of these, let's say, recent developments, like our understanding of quantum reference frames and so on, one may question whether the frameworks we are using are actually suitable for that. Because one could say, okay, if you have a quantum reference frame, to still talk about classical inputs and outputs in a more or less absolute sense may not fit. Or maybe to put the question in different words, could it potentially be that people in the year 1902, when this citation was made, actually could have had a reasonable framework that would prepare them for quantum theory?
Yeah. I don't really have like a full like comprehension or vision of what are all of the different possibilities that you could that you would need to tackle in order to be fully prepared. But I think that how to put it in words?
Sorry, it was a very general question. So
yeah.
Maybe it's something for the discussion later.
No, it's a very good question. I would be really happy to discuss more about it. But the thing is that if we need to give up the quantum framework to begin with, before we can like redefine a theory for physics, then the kind of things that we have at the moment will not be valid anymore in full generality. So like this kind of very first naive approach is to say, well, I will not assume that the quantum framework is valid, but I will still somehow endorse some notion of space-time where events are localized in this space-time, and the no signaling principle, it makes sense to think of causality in the arrow of time, and parties being able to perform space-like separated actions such that the no signaling principle is endorsed. So it's like I am not relaxing everything, I'm just relaxing the quantumness of the setup and still endorsing that. It is possible that that cannot be endorsed anymore in a full theory that is compatible with general relativity. But that is a different question, like how to make sense of these experiments, even if you do not assume a notion of space-time, is something that I'm not intending to address in this kind of approach.
Is it on? Yeah. So actually, I had an idea in response to what Renato said, which was that I could imagine that, maybe a world in which, Lewis Carroll invented finite dimensional GPT theory just as a fun thing to play around with. And I don't know, we can ask whether that would have helped prepare us for quantum theory or not. But the question I wanted to ask Belen was, so many of these post-quantum theories, and in particular the ones with square state spaces that are used in PR boxes, and probably a lot of similar ones, have what you might call multiplexing, where you can store, for instance, 2 bits of information in one PR box system, one wing of a PR box, and then the person who reads it out can decide which bit to get. And you can't do that in quantum theory. So that, I don't know if anyone's linked that principle very tightly. I kind of think they have, to reducing the amount by which you can violate Bell inequalities. But I wonder if it could be a principle also that could help limit the amount of steering. I don't know what the relation is offhand.
Yes, I haven't really thought of that, so I don't really have a comment at this moment, but it would be good to talk about that later. I don't know if, John, do you have anything to comment on that? No.
Isn't this information causality?
Yes, that information causality is one way of stating this principle, yeah. So it's been related to Bell inequality violations, but maybe also steering, I don't know.
Yeah, so the question would be to how to use information principles like information causality to understand the limits of steering in a world where that principle is fulfilled. But I wouldn't really know how to do it in the sense that, I mean, it would be really good to talk about it if you want this week, but like Constantinos was saying before, there is this thing of how to somehow keep the information in a way of the fact that Bob has a particular quantum state of a certain type in his lab. So how that information can be somehow incorporated into the definition of a principle like information causality. Because at the end of the day, these kind of things is about how much, if you like have a classical input and you want to guess a particular message that is being sent, and how much you can retrieve by the information that is being sent. It's all kind of classical variables. And at the end of the day, I have the feeling that if we only focus on that, we will somehow lose the fact that there is some quantumness in a steering experiment. So I would be really interested to see how, or to discuss, if you want, how this could be somehow kept track of during like that sort of analysis. Mm-hmm.
Yeah, thanks.
So I've seen that there are more questions, but we're a bit over time. So I would ask you to ask Ana Belen in the break, and we can thank our speaker again.